In this video, I'm going to continue to look at chemical reactions, but I'm going to target double replacement reactions. This is one category that you already have some experience with, as in the first semester we looked at some water testing labs and we looked at precipitation reactions, which are double replacement reactions. In this video, though, we will look at the full spectrum of double replacement reactions. So a double replacement reaction is going to take place, and it's going to happen in an aqueous environment, in aqueous solution. So you will have ionic compounds that are dissolved in water, and we're going to mix them together. So you will have a reaction between two ionic compounds. So when you see that, you know that's what is about to take place, or potentially will take place. And in these double replacement reactions, again, this is one of those names that is descriptive of what's actually going to happen. And that just means that the compounds, the ions that make up the compounds, they're going to essentially trade places. They're going to exchange partners. But for double replacement reactions to happen, certain things must take place. Otherwise, you just end up with a mixture of a bunch of ions in water. And so there are certain minimum requirements that would have to be met to know in your prediction whether that really reflects what happens in reality. So when I say requirements, remember, what I mean is these are patterns that chemists have identified by studying hundreds of reactions and understanding what is the pattern that emerges when certain chemicals are mixed together. So this isn't like we're just arbitrarily deciding what should happen. We're predicting what nature is actually going to execute when we mix things together. So there are really three possibilities, one of which must take place in order to properly identify the reaction having occurred. The three possibilities are, first, you'll get the formation of a precipitate. You would see that upon mixing the solutions, it turns cloudy, just like you saw back in the labs that we did back in the first semester. But there are two other possibilities that we haven't run into before. Or you might secondarily get the formation of water. And we'll see which circumstances would have to be met in order for water to form. We haven't seen that before. Or a third possibility, you get the formation of a gas. And memory serves me, when we did the grid experiment, if you remember one combination, we actually did see bubbles forming. And that told us that obviously the bubbles represented a gas, and that would have indicated that a reaction had indeed occurred. So let's look at these three possibilities and see how you would be able to complete the equation and write out a balanced equation. So let's look at precipitate reactions. So again, you know a precipitate is really a solid forming. So if you mix two ionic compounds in aqueous solution and it turns cloudy, that cloudy material is the solid, or the precipitate. And we know that what must have happened with the chemicals we mixed, that the ions switched and they joined up with a new partner, and then we would write the formulas of the new compounds, again, utilizing things that we already know, skills that we already know, relying on their oxidation states to come up with the correct formulas. To identify what is actually the solid or the precipitate, then we would refer to our solubility chart, again, as we did back in the first semester. Whatever is found to be insoluble, then that must be the cloudy material. And if you remember from your grid experiment, man, we can get all kinds of different colors of precipitates. Here you just see white and yellow or gold, but we saw blues and purples and a whole variation of colors that emerged depending on what ions we actually had mixed together. In situations where no precipitate forms, obviously we don't get any cloudiness detected. It's not even murky to any extent, and therefore the reaction would not have taken place. And we saw that again on your grid experiment, where there were several combinations in the little grid, the little squares, where it just essentially remained clear, and that told us that we just had a mixture of a bunch of ions. No new materials were produced. So how do we write the equations that represent a precipitation reaction? So let's go through a couple of examples and see, how do you recognize it's going to be a double replacement reaction, and how does that help us write the equation? So here's the situation. We've got a silver nitrate solution, and we're going to pour that into a beaker that contains a potassium sulfate solution, and we're going to try to decide whether a reaction does happen, and if it does happen, we're going to write all the correct formulas for the reactants and products, and then we're going to balance it. So silver nitrate, AgNO3, so silver is 1 plus, nitrate is 1 minus. There's the correct formula. Remember, AQ tells us it's dissolved in water. Potassium sulfate, so potassium group 1, 1 plus, sulfate, polyatomic 2 minus, K2SO4, also in solution. So we put AQ. I'm going to go ahead and switch them, switch partners. So Ag and potassium, silver and potassium, we're going to switch places. So silver joins up with sulfate. I look at their oxidation states. I get the right formula. I do the same thing with potassium and nitrate matched up. Got its correct formula. And then I had to go back to my my solubility chart, and I found out that, in fact, I did get a precipitate. Silver sulfate is not soluble in water. So I know this reaction will, in fact, happen. Okay? And I've got all my correct formulas, but I notice that it's not balanced, and I go in and I balance out things by putting in a couple of new coefficients. So I wrote out the equation as if it really happened, and I noticed that, in fact, I did get a precipitate, so I knew one of the criteria for a double replacement reaction was met. I got something that was insoluble. So if I mix these together, in fact, it would turn cloudy, the mixture. And the cloudy material, the solid, would be silver sulfate. Let's look at a second example of a potential precipitation reaction. So we got copper chloride solution is mixed with a ferric nitrate solution. I have to decide whether a reaction happened and then write out a balanced equation. So copper 2 chloride, copper 2 is 2 plus, chloride is a halogen, 1 minus. There's my correct formula, CuCl2, it's a solution, AQ. Ferric, I know, is 3 plus, nitrate is a polyatomic, it's 1 minus. There's my correct formula, FeNO3, 3, it's a solution, AQ. I then write out the products as if this is really going to happen. The iron and the copper switch places. I get the formulas of the potential products. But this time, different from my first example, I find that both combinations end up being soluble. In other words, I don't get a precipitate. So I know that in reality, I know if something is in solution, that those ions really are dissociated. I just would have a mixture of these 4 ions and nothing new will have formed. It will not have turned cloudy. So I realized that, in fact, no reaction happened. I simply have a mixture of these 2 ionic solutions. So that's why you need to use your solubility chart. You write the equation, you complete it as if you think it's going to happen, but you have to check on the solubility to determine if, in fact, it led to something new. In my second example, in fact, that didn't happen and no reaction would take place. So precipitation reactions, you have to use your solubility chart. Now, there are 2 other types of double replacement reactions I referred to in my introduction to this video. Let's look at 2 examples that illustrate those possibilities. Here I've got, lithium hydroxide solution is mixed with a sulfuric acid solution. And again, I'll have to see whether one of my 3 criteria will be met. Well, lithium hydroxide, lithium is 1 plus, hydroxide is 1 minus. There's my formula, LiOH. It's in solution, AQ. Sulfuric acid, I look up. I know that's the same as hydrogen sulfate. Hydrogen is 1 plus, sulfate is 2 minus, so H2SO4. It's in solution AQ. Two ionic compounds, aqueous solutions. Let's switch partners. Li hooks up with sulfate. Lithium is 1 plus, sulfate is 2 minus, so Li2SO4. And I look up on my solubility chart and I see that that is soluble, so AQ. Hydrogen hooks up with hydroxide. Well, H is 1 plus and OH is 1 minus, so HOH would be the formula, but I know HOH really is just simply water. So I did meet one of my criteria. So one type of double replacement reaction, we get water forming, and it, of course, is a liquid. So this is my correct skeleton equation. I go through and I balance it, and there's my balanced equation. So you get water forming essentially when you have an acid and a base react. When you see a compound with hydroxide ions, you know that that's a base. So LiOH is actually a base. And of course, sulfuric acid, having the hydrogens, makes it an acid. When acids and bases react, they neutralize each other and they form water. And that is the driving force behind this reaction actually happening. So I didn't get a precipitate, but I got water forming. I met one of my criteria. Let's look at another example. Sodium sulfide solution is mixed with a hydrochloric acid solution. So we're going to see if this happens. So sodium is 1 plus, sulfide is 2 minus from group 6. So Na2S, it was a solution, AQ. Hydrochloric acid, I look up, is the same as hydrogen chloride. 1 plus and 1 minus gives me HCl. It's a solution, so I put AQ. Two ionic compounds in solution, they're going to switch partners. Na, sodium, hooks up with chlorine, 1 plus and 1 minus. I know sodium chloride is just simply salt. Of course, it's soluble, AQ. Hydrogen hooks up with sulfur, hydrogen 1 plus, sulfur 2 minus, so H2S, and I realize that hydrogen sulfide is a gas. I would see bubbles forming, so I met a different criteria. A gas formed, and that's what's driving this reaction. So it does happen. That's the correct skeleton equation, but I notice it's not quite balanced, and I go back in and I balance it. All right, so we see that there are other double replacement reactions other than precipitation reactions. The formation of water is one of the new criteria that we examined in this video. Those are going to occur essentially when you have acids and bases reacting. We'll talk about this more later on when we talk about acids and bases. And another one is the formation of a gas. And you actually saw this again in one of your little grids when you mixed some of your solutions together back in the precipitation lab. We did see bubbles form. So gases forming can also indicate a double replacement reaction has in fact occurred. So double replacement, two ionic compounds in water mixed together, you get either a precipitate or water forms or a gas, and the reaction does take place.